Hello to everyone, my name is Nilo and today I'm going to present you KARONTE, detecting insecure multi-binary interactions in embedded firmware. This project is a conjoint effort between me and several of my colleagues from University of California, Santa Barbara and Arizona State University. IoT devices are everywhere and they span from smartphones to wearables such as smartwatches and so forth. A study conducted in 2019 on 16 million households shows that more than 70% of homes in North America have an IoT device. IoT devices use and collect our data, and some data is more sensitive than other. Therefore, we wonder, are IoT devices secure? Well, unfortunately, IoT devices are not secure. For instance, in 2019, the malware Silex bricked 4,000 insecure IoT devices, making them unusable. And still in 2019, researchers found that 2 million IP cameras have vulnerabilities that could allow attackers to spy on the camera owners. So why is it hard to secure IoT devices? IoT devices are very diverse. They might mount very different architectures, for instance, ARM, MIPS, x86, and so forth, and sometimes these architectures are even proprietary. Also, IoT devices manage external peripherals, which usually use custom code. The firmware in IoT devices can be Linux-based or a blob firmware. Linux-based firmware are by far the most common. Studies show that 86% of firmware are based on Linux. On the other hand, blobs are usually operating systems and user applications packaged together in a single large binary. Also, firmware are usually made of multiple components. Let's see an example. Usually when we communicate with our IoT device, we use our phone, we send a request, which will be received by the first component in the firmware of the IoT device. This component, the web server in this example, will take the request, will do some elaboration, and it might share some data with another component, or the Android binary in this example, which will take the data, elaborate the data, send back the answer to the web server, which finally will send back the response to our smartphone. So why is it hard to secure IoT devices? Well, because in practice they're very diverse. Of course, there have been a great effort in the community to secure IoT devices. However, current tools based on dynamic analysis are usually hard to apply due to the customized environments of the IoT devices. And current tools based on static analysis, they use what we call the single binary approach, which, as we will see soon, might produce two many false positives. Let's see an example of this behavior. This example is based on a true case that we found in our firmware, in our dataset. As we see, the web server, when it receives a request, parses the requests, it extracts some data, and then it sets this data into an environment variable called query string, and then it eventually spawns another binary. Now, if you see, the data that is being parsed, if it contains some known keywords, it's just returned. Otherwise, it's constrained to be at most 128 bytes. When the Android binary is spawned, first it retrieves the user data through the environment variable query string, but it also gathers some other system data through the environment variable called logpath. And then it processes the requests. The Android binary first checks if the user data contains some no strings, and if so, copies both the user data and the system data into two different stack variables. Now, if you see, if the user data is larger than 128 bytes, we might have a buffer overflow at line 6, while we should not have any buffer overflows at line 7, as we can assume that system data is well handled. During our presentation, we're going to refer to the first type of binaries as setter binaries, as are those that prepare some data for other binaries to be used, while the second type of binaries will be called ender binaries. So though in this example we only had possibly one false positive, we can easily imagine how on a large firmware these false positives might rise. So how these different components actually communicate? They do so through what it's called inter-process communication, or IPC, which basically it's a finite set of paradigms such as files, MMIO, sockets, and so forth. An actual communication between two binaries is represented by what we call data keys, which is the endpoint where such data will be available for retrieval. In the example before, a data key was the environment variable query string. Now, each binary that relies on some shared data must know in advance the endpoint where such data will be available, which means that data keys are usually hard-coded in the program themselves. Therefore, in order to find bugs in firmware in a precise manner, we need to track how user data is introduced and propagated across the different binaries. Let's see our tool. KARONTE is a static analysis tool that tracks data flows across multiple binaries to find vulnerabilities. First, KARONTE finds the binaries that introduce user input into the firmware, as the web server in the example before. We call those binaries border binaries, are those binaries that interface the firmware to the outside world. Then KARONTE tracks how data is shared with other binaries within the firmware sample and builds what we call the binary dependency graph, or BDG. Then KARONTE finds how data is shared with other binaries within the firmware sample using the BDG, which means that KARONTE understands what constraints are applied to the data that has been shared. Finally, KARONTE detects vulnerabilities that arise from the misuse of the data. This is an overview of our system that we will explain in detail next. KARONTE takes a packed firmware, unpacks the firmware, finds the border binaries between the firmware, and then it builds the binary dependency graph. The binary dependency graph, as we will see, is built built with a set of modules that we called CPF, or Communication Paradigm Finders. And then it is used by the multi-binary data flow analysis module and insecure interaction detection in order to find vulnerabilities and generate alerts. So as mentioned, the first step, KARONTE unpacks the firmware image using the off-the-shelf firmware unpacking utility Beamwalk. Then KARONTE has to find border binaries. In the context of IoT, we define a border binary, a binary that receives some data from the network and contain parsing capabilities to validate users' requests. To find binaries that contain parsing capabilities, we based our algorithm on the related work, and we collect three different quantities: the number of basic blocks, the number of memory comparisons operation, and the number of branches. Since we're interested in finding functions that parse user data that is received from the network, we also introduce two new quantities. We count the network-related keyword referenced within a function, and then we search if there is a data flow between a read from socket and a memory comparison operation. Then we use all these quantities to compute what we call the parsing score, which basically is the likelihood that a function contains parsing capabilities and is parsing data that is coming from the network. Then we compute the parsing score for each binary as the maximum parsing score of its functions. Eventually, we cluster the binaries using their parsing scores and the DB-scan algorithm, and consider the cluster with the highest parsing score as the set of border binaries. Then we build the binary dependency graph, which again represents the data dependency among the binaries in a firmware sample. Let's see the BDG algorithm. We start from the identified border binaries, and then we take the data that is compared against network-related keywords and run a taint analysis to detect whether the binary relies on any IPC paradigms to share some data. If so, we establish if the binary is a setter or a getter. We retrieve the employed data key, and then we scan the firmware sample to find other binaries that rely on the same data key and schedule them for further analysis. During the BDG algorithm, the IPC paradigms are detected through a set of modules named CPF. We design each CPF to identify a particular IPC and a binary role, which means setter or getter. A CPF also finds other binaries that rely on the same data key within the firmware sample. And finally, we provided KARONTE with a generic CPF to cover those cases where the IPC is unknown. For instance, in those cases where symbols are stripped from the binary. The intuition behind this generic CPF is that the data key must be used as index to set or get some data, as we can see in the last line of in the example of this slide. Let's see how the BDG algorithm works with an example. When KARONTE analyzes the function serve request, it will follow the data flow and inspect the function parse URI. Here we can see that some data is compared against some network-related keyword, and therefore KARONTE will taint the variable p. Now if we see the taint is carried out outside the function, and the variable data line 11 will be tainted. As such, the argument of the setenv call line 12 will contain tainted data, and the environment CPF will understand that some data is shared across the environment. The environment CPF also will extract the data key used query string and identify this border binary as a setter binary. Then we will use the query string data key to find other binaries that rely on the same data key and schedule them for further analysis. Then we build the BDG by creating an edge between a setter and a getter for each data key. The multi-binary data flow analysis module uses the BDG to find and propagate the data constraints from a setter to a getter. In order to keep the analysis tractable, we only apply and propagate the least strict constraints. In our example, we could see that the variable data was tainted because of two different program paths coming from the function parse URI. Now, if you see, the first path, line 4, contains unconstrained data, while the second one contains constrained data. As such, we only consider the first set of constraints, in this case the empty set of constraints, and propagate this set to the getter binary, which will provoke the variable query line 12 in the getter binary to be unconstrained. Then we run a static taint analysis and check whether tainted data can reach a sink in an unsafe way. In this context, we consider sinks memcopy-like functions, which means that functions that implement memcopy-like semantically equivalent code, the reference of a tainted variable, and comparisons between tainted variables in loop conditions to spot QoS vulnerabilities. So, continuing with our example, we know that query now contains tainted data, and tainted data is passed to the function process request. In this function, we can see that a memcopy-like function, it's called, and it's using some tainted data in an unsafe way. As such, we generate an alert. Our taint engine is based on Bootstrap, which is based on symbolic execution. Okay, let's see the evaluation. We evaluated KARONTE using two data sets. The first one, composed by 53 latest firmware samples from 7 vendors, and the second one, composed by 899 firmware samples gathered from the related work. We can see that across the 53 firmware samples analyzed, we analyzed in total more 8,000 different binaries, and our system produced 87 alerts. Of these, we found that 51 were true positives, and there were indeed bugs. It's interesting to note that 34 of these 51 bugs were found because we were propagating user data across different binaries. We investigated each alert, and we found that 46 of them were previously unknown software bugs, and 5 of them were already known. We disclosed all of our funding to the vendors. This is our large-scale evaluation. Understand that there is a lot going on this table, but we'll see some summary of these numbers in the next slides. Overall, we analyzed 899 firmware samples, and we found that almost 40% of them are multi-binary firmware samples, which means that users' requests are handled by different binaries in the firmware sample. Overall, we analyzed more than 140,000 binaries, And our system produced a few more thousand alerts. We investigated 100 alerts picked randomly, and we found that 44 of them to be true positives, as user-provided data reached a sink, and 30 of them to be multi-binary vulnerabilities. Finally, we registered KARONTE performances, and we found that, as we can see in figure A, 80% of the firmware samples were analyzed in a day, and also that they shown a great variance, which we found to be due to some implementation details. For instance, anger in some cases would take up to 7 hours to be the CFG. Also, as we can see from figure B, the number of paths do not heavily impact on the total time. And as we can see from figure C and D, the performances are not affected by the size of the firmware, are not greatly affected by the size of the firmware. And after this, I will take any questions, and thanks for the attention.